Hey there. Ever wondered how scientists and AI systems stay confident when working with incomplete information? Today, we're diving into a groundbreaking technique called Prediction-Powered Inference, PPI, and how it's transforming how we turn guesses into reliable conclusions. Let's break it down. Here's the challenge. In fields like healthcare or finance, labeled data, like patient outcomes or stock prices, is expensive and scarce. But we do have tons of unlabeled data. Think of it as a vast pool of raw information. Machine learning models can predict labels for this data, but those predictions aren't perfect. The big question is, how do we use these imperfect guesses to make statistically valid conclusions? That's where prediction-powered inference steps in. Imagine you're estimating the average effect of a new drug. Traditionally, you'd only use the small set of labeled data you have. But PPI uses ML to guess labels for the rest of the data, then adjusts for the errors in those guesses. This makes your confidence intervals, those ranges that tell you how sure you are about your estimate, more precise, without losing reliability. But here's the twist. Most PPI methods work for a fixed dataset. What if you're collecting data over time, like monitoring a patient's health daily or tracking stock market trends? You need confidence intervals that stay valid no matter when you check them. That's where this new research shines. The team extended PPI to a sequential setting. Think of it like a real-time dashboard. They used a mathematical tool called Ville's Inequality, which acts like a reliability check for probabilities over time, and a technique called the method of mixtures, like combining different sources of information to get a more robust result. This lets them create confidence sequences, intervals that stay valid as new data arrives, not just at a single point in time. Here's the magic. They also incorporated prior knowledge about how good the machine learning predictions are. If the model is really accurate, the confidence intervals tighten up, giving you more precise results. It's like having a trusted advisor who knows the model's strengths and weaknesses, so you can adjust your conclusions accordingly. Let's unpack this with a simple example. Suppose you're tracking customer satisfaction for a new app. You have a few survey responses, labeled data, and a huge pile of app usage data unlabeled. A machine learning model predicts satisfaction scores for the usage data. PPI uses those predictions to build a confidence interval for the average satisfaction. But instead of just checking once, this new method updates the interval as more data arrives, always keeping it reliable. The results? In both real-world and simulated tests, this approach outperforms traditional methods, especially when predictions are good and data grows over time. It's a game changer for applications like online learning, real-time monitoring, or adaptive experiments where decisions need to be made on the fly. So what's the takeaway? By combining machine learning predictions with clever statistical techniques, we can make better use of limited data while keeping our conclusions trustworthy, no matter how long we've been collecting information. It's a powerful reminder that sometimes, the best science isn't about having all the answers, but knowing how to ask the right questions with the tools you have. Thanks for watching. If you want to dig deeper into the math or see how this applies to your favorite tech, hit that subscribe button and let me know in the comments. Stay curious.